So the amazing thing is that the physical process that's behind all of these different phenomena is the same, and it's called the random walk. So the idea of a random walk was first invented in the scientific literature, at least to my knowledge, by a great statistician by the name of Karl Pearson, who in the early 1900s wrote an article to Nature in which he called The Problem of the Random Walk. And in it, he asked the readers of Nature, which is one of the great scientific journals of our time and was also of his time, the following question. He said, suppose you have a person who decides to take a random step to the right or the random step to the left. So the idea is that at every step, what we're going to do is flip a coin. If the coin comes up heads, I will take a step to the right. If the coin comes up tails, I will take a step to the left. And then I will continue with that process. I'll flip a coin, take a step to the right, flip another coin, and take a step to the left. And Pearson asked what the behavior of this person undergoing this walk would be like, and in particular, could someone come up with a mathematical description of it? So this random walk, the idea that Pearson has described, has since then been sort of colloquialized as the drunkard's walk, the idea being that this is something that a drunkard might do, take a step randomly to the right and then take a step randomly to the left. Now, it turns out that if Pearson actually had been a careful reader of the scientific literature at the time, he would have found out that this question had already been answered, not once, but twice, in two entirely different contexts. I'm going to tell you the second solution first. The second solution was by a person that most of you have heard of, a young man by the name of Albert Einstein, who wrote what was arguably his most important scientific paper in 1905. And the paper had a title which is so boring that when I tell it to you, you will likely fall asleep. Namely, it was called On the Movement of Small Particles Suspended in Stationary Liquids Required by the Molecular Kinetic Theory of Heat. It sounds terrible. But what Einstein did in this paper was to describe a random walk. He basically argued that perhaps molecules were undergoing a random walk. And indeed, in his paper, he even talked about the fat globules in milk, which we've just described, because he thought that these might be things that you could see under a microscope and watch them sort of randomly walk around. And what Einstein did, and the reason that he was so interested in this, is that he felt if you were to characterize this motion of the fat globules in milk, that you might be able to calculate the size of a molecule, or measure really the size of a molecule, which had been as yet unmeasured. So that was the second example in the literature, the second solution in the literature that I'm aware of describing a random walk. The first was actually a couple of years earlier, and this was by a person that probably none of you or very few of you have heard of, a young man by the name of Bachelier. Bachelier was a student of Poincaré, who was one of the great mathematicians of the 19th century, and he was interested in the dynamics of stock prices. His PhD thesis was on the problem of how is it that a stock price, like the price of IBM or Apple or whatever your favorite stock happens to be, how does that change with time? And he argued that actually that what happened from one day to the next was sort of random. Namely, the stock price underwent a random walk. And he invented a mathematical description of the random walk, which was really identical to that which Einstein described in his paper on the molecular theory of heat, and which we are about to describe to you right now. So what is a random walk? So I already described to you the process. You have a person, and the person basically flips a coin and then takes a step to the right or to the left. If the coin is heads, you go to the right. If the coin is tails, you go to the left. If I had more room in front of this camera, I would sort of move off the camera, moving to the right. I would come back on the camera, moving to the left. And the question for you is if I flip the coin, I don't know, say 100 times, where am I likely to be? So why am I telling you this? I want you to go back to one of the examples that we just described. And since we're discussing spherification now, let's think about that. So what we have, remember, is this drop of very tasty mango juice. Within it, there are these charged alginate polymers. And on the outside, we have calcium ions. And so what we're going to do now is describe the motion of the calcium ion. So you're a calcium ion on the outside, and what you see is on this side, all of this alginate. And so what you do, you flip a coin and you either move back to your friends, the calcium, or you move into the alginate. So you move into the alginate. So now we have a calcium molecule in the middle of the alginate. The calcium can then decide to move to the right or to the left, and all the calcium molecules are doing this. So over time, you have all of these random walking calcium molecules, molecular drunkards, that are basically undergoing these little steps into the shell. And some of them happen to bang into the alginate molecules, causing the strands to stick together. And that is what forms the spherification shell. the same thing, of course, happens when we think about the experiment with vinegar moving into milk. In this case, you can replace my words that I said for the calcium ions with the vinegar molecules, which are, of course, moving into the milk, undergoing the random walk, and sometimes bumping into the milk and causing it to stick to each other. So the question that all of these processes raise is, how far do the calcium ions get? How far does the vinegar get? This isn't an abstract question when you think about it in terms of food. It is really a question of how much of the shell, how thick is the shell going to be? Like if I wait for a time t, right, t seconds, like say I wait for 10 seconds, how thick will the shell be? So it turns out that both Bachelier and Einstein invented a formula which describes what the thickness of the shell is. And it's related to a fundamental constant that is a property of the material that is undergoing the random walk, which scientists call the diffusion constant. And this formula that they invented is our equation of the week this week. So as you all know, we all have to clap when there's our equation of the week. And so here it is. And so I'm going to clap. I think I'm allowed to do that. So this equation is, I will just read it to you. It says that L, which is the length that the calcium has moved, it's the distance that the milk has solidified, turned into cheese, and that's a length that's measured in something like meters or centimeters or some unit of length. That's equal to the square root of 4 times d times t, where t is the amount of time that's elapsed in seconds and d is the diffusion constant, which essentially characterizes the random walk. For different processes, this diffusion constant is different. D changes whether you're looking at the motion of heat into a food or the motion of calcium into a spherification droplet, or the motion of vinegar into milk. So for calcium ions into water, the magnitude of D, it turns out, is 8 times 10 to the minus 10 meters squared per second. And so what's very nice about this is that using this number and indeed this formula, we're now going to be able to calculate how thick the spherification shell is as a function of how long you wait. So let's use this just to see how it works. So if we were to say that we wanted a 1 millimeter shell, which is, it's a bit of a thick shell, but it's not so thin. And we were to use this formula, L equals the square root of 4dt, then what we can do is square both sides of this formula. So we can write L squared equals 4dt, and we can then solve for t, which is the time that it takes for a thickness of length L to form. So if we do this, we end up with a formula that the time that you have to wait is L squared over 4d. So if we put in numbers, if we put L as a millimeter, which is 10 to the minus 3 meters, and we use the diffusion constant of calcium ions in water, we find out that it takes about 300 seconds for this to happen, which is about 5 minutes. So according to this model, if you would like there to be a 1 millimeter shell in your spherification, you should wait 5 minutes. So the power of this formula is that it explains on the basis of the physics of the problem how the thickness, which is what you're measuring, is related to the time that you have to wait. And we will see in subsequent lectures how this very same formula will lead us to simple estimates for how long to cook a steak, or how long you should cook a lasagna, or how long you should wait if you were happening to make your ricotta cheese between 2 cover slips, which no one actually does. So I'm a bit silly. But this formula really is the fundamental equation that describes how one thing diffuses into another and really plays a central role in cooking.